Hello and welcome to the Slow Wave Science channel. We are glad you found your way here. Do you like falling asleep to deep thoughts and facts about science? Tonight's journey is for you. There is nothing for you to do but relax, listen, and enjoy. Tonight we drift through the Milky Way. The Milky Way. Understanding our home galaxy. Introduction. When we gaze up at the night sky on a dark evening, away from the glare of city lights, we witness one of the most profound sights available to the human eye. A luminous band stretching across the heavens like a river of light. This ethereal path is the Milky Way, our home galaxy, and it represents one of the most fundamental facts about our place in the cosmos. Despite being something our ancestors observed for millennia, the true nature of this galactic band eluded humanity until the 20th century. Today we understand that the Milky Way is far more than just a beautiful night sky phenomenon. It is a vast rotating disk of stars, gas, and dark matter, containing hundreds of billions of stellar objects, including our own Sun. Understanding the basic identity of the Milky Way, its structure, size, composition, and the very words we use to describe it, provides essential context for appreciating our cosmic neighborhood and humanity's place within it. The structure. A barred spiral, not a simple spiral. One of the most important details about the Milky Way's identity is its precise structural classification. For much of the 20th century, astronomers described the Milky Way as a spiral galaxy, and while this designation captures something essential about its overall form, it is incomplete. The Milky Way is actually a barred spiral galaxy, a distinction that may seem technical but fundamentally defines how the galaxy is organized. A barred spiral galaxy contains a prominent linear feature, a bar of stars and material, extending across the galactic center. From this bar, spiral arms sweep outward in a pinwheel pattern. The presence of this bar is not merely a cosmetic detail. It has profound implications for how the galaxy evolves, how matter circulates within it, and how stars form in different regions. The bar's gravity influences stellar orbits and guides the movement of gas clouds, creating conditions that promote or inhibit star formation depending on location. Our Milky Way's bar is particularly prominent, extending approximately 27,000 light-years in length and oriented at roughly a 45-degree angle relative to our perspective from Earth. Recognizing this barred spiral structure distinguishes the Milky Way from other types of galaxies and reflects our increasingly sophisticated understanding of galactic dynamics derived from infrared observations and detailed stellar mapping. Our home galaxy and its contents. The Milky Way's most fundamental identity marker is that it is our home galaxy, the vast stellar system that contains not only the Sun, but also our entire solar system with all its planets, moons, and smaller bodies. This simple fact carries profound philosophical weight. For almost all of human history, observers assumed that our Sun and Earth occupied a central or uniquely important position in creation. It was only through centuries of careful observation and calculation that we came to understand Earth's true position. A small rocky planet orbiting an ordinary star, the Sun, which itself is a fairly typical middle-aged star located within one of the spiral arms of a medium-sized galaxy. The Milky Way is home to an estimated 100 to 400 billion stars, though more recent estimates often cite around 200 to 400 billion. Beyond stars, the galaxy contains vast clouds of gas and dust from which new stars continually form, supermassive black holes at its center, neutron stars, planetary systems, and enormous quantities of dark matter, the mysterious substance that outweighs all visible matter combined. The diversity of objects and phenomena within our galaxy rivals the diversity of any ecosystem on Earth, yet spread across incomprehensible distances and spans of time. Understanding that we live within this galaxy, not outside observing it, fundamentally shapes how we understand our cosmic context. The visual phenomenon, a hazy band of light. When we look at the Milky Way from a dark sky location on Earth, we observe it as a hazy, cloudy band of light stretching across the night sky. This appearance, visible to the naked eye on clear nights, puzzled observers for thousands of years. What appears to our eyes as a luminous mist is actually something far more structured and magnificent. The combined light of billions upon billions of distant stars, too faint to be distinguished individually from Earth. Imagine standing within a vast, thin disk of stellar objects and looking toward the plane of that disk. The density of stars increases dramatically in that direction, creating an apparent brightening, where we look along the galactic plane rather than perpendicular to it. This geometric effect, combined with the fact that individual stars are too distant to resolve separately, creates the visual impression of a continuous, cloudy band rather than discrete points of light. As telescopes have improved, astronomers have been able to partially resolve this band into its constituent stars, confirming that what appears as a nebula to the unaided eye is actually a stellar population so dense that their combined light merges into a unified glow. This revelation exemplifies how improving observational tools have repeatedly transformed our understanding of celestial objects from mysterious phenomena into comprehensible physical structures. Dimensions, from classical estimates to modern refinements. For much of the modern era of astronomy, the Milky Way's visible disk was estimated to span approximately 100,000 to 150,000 light-years in diameter. These dimensions represent the extent of the galaxy, where the disk of stars, gas and dust is readily observable and measurable. A light-year, for context, is approximately 5.9 trillion miles. The distance light travels through the vacuum of space in 1 year. Even within a relatively nearby galaxy like ours, such distances are so vast that they transcend human intuition. To traverse the Milky Way's disk at the speed of light, the fastest possible speed in the universe, would require 100,000 to 150,000 years of continuous travel. However, more recent astronomical surveys and analytical techniques have challenged and expanded these classical estimates. Sophisticated observations using modern telescopes, including infrared and radio observations that penetrate dust clouds blocking visible light, have suggested that the Milky Way's full extent may reach 200,000 to 256,000 light-years in diameter, when faint outer regions and galactic halos are included. These extended reaches contain sparse populations of older stars and dark matter that are difficult to observe but contribute significantly to the overall galactic structure. The expansion of the Milky Way's measured size illustrates an important principle in astronomy. Our understanding of the cosmos is not static, but continuously refined as observation techniques improve and new data becomes available. What was once considered the complete galaxy's boundary is now understood as merely the visible, bright core surrounded by more diffuse but still significant outer regions. Cosmic mass, 1 trillion suns worth. Perhaps one of the most staggering facts about the Milky Way's basic identity is its total mass. Current estimates place the galaxy's mass at roughly 1 to 1.5 trillion times the mass of our Sun. To put this in perspective, a single trillion is the number 1 followed by 12 zeros. Multiplying the Sun's considerable mass, which would take approximately 333,000 Earths to equal, by this factor produces a number so large that it exists at the threshold of meaningful human comprehension. This enormous mass is not distributed evenly or even primarily among stars, despite their tremendous individual masses. Roughly 90% of the Milky Way's mass consists of dark matter, an invisible substance whose nature remains one of astronomy's greatest unsolved mysteries. Dark matter's existence is inferred from its gravitational effects on visible matter and the dynamics of galactic rotation, but it does not emit, absorb, or reflect electromagnetic radiation, making it impossible to observe directly with conventional telescopes. The remaining roughly 10% of galactic mass is ordinary matter, the atoms and molecules that comprise stars, planets, gas clouds, and all visible structures. This distribution reflects a profound truth about the universe. What we can see and study directly represents only a small fraction of what actually exists. The galaxy's tremendous mass generates the gravitational field that holds billions of stars in their orbits, maintains the integrity of the spiral structure, and influences the motion of gas clouds across billions of years. Etymology, from Latin rhodes to Greek cosmic origins. The very name Milky Way encodes the observations and classifications of ancient and classical civilizations. The term derives from the Latin phrase Via Lactea, which translates directly as Milky Road. To ancient Romans and other classical observers, the appearance of the galactic band resembled a road or pathway marked by milk, a white, luminous feature traversing the darkness. This poetic description reveals how our ancestors perceived and mentally organized the night sky, seeing in it familiar earthly features like roads and paths. The Greek equivalent term, galaxias kyklos, meaning roughly milky circle, provided the etymological root for our modern word galaxy. This linguistic connection illustrates an important principle in science. Terminology often preserves the historical context of discovery and observation. The word galaxy itself, applied today to billions of vast stellar systems spread throughout the universe, originated from the Greeks' naming of the specific white band visible in our own night sky. Only later, after telescopes revealed that spiral nebulae like Andromeda were in fact separate island universes of stars beyond the Milky Way, did astronomers generalize galaxy to describe all such systems. Scale and perspective. A medium-sized giant. Despite its staggering size and mass, the Milky Way holds a somewhat humbling position within the broader cosmic context. It is classified as a large spiral galaxy, yet it is not a giant among galaxies. Giant elliptical galaxies, which constitute a small fraction of all galaxies but contain the most mass and stars, dwarf the Milky Way substantially. Messier 87, a giant elliptical galaxy located in the Virgo cluster, approximately 55 million light-years away, has an estimated diameter of perhaps 260,000 light-years and contains roughly 100 billion stars. Other giant elliptical galaxies surpass even these figures. This perspective, that our Milky Way, despite its billions of stars and trillion solar mass structure, is medium to large rather than among the true cosmic giants, exemplifies the theme of cosmic humility that recurs throughout astronomy. Each successive revelation about the universe has reduced human significance in purely physical terms, yet has simultaneously expanded our understanding and deepened our connection to the broader cosmos. Recognizing that the Milky Way is large but not largest, massive but not most massive, situates us appropriately within a cosmos far exceeding any single object's dominance. The stellar population of the Milky Way, structure, diversity, and cosmic history. The Milky Way is not merely a backdrop of glittering points in the night sky. It is a vast, dynamic ecosystem of stars, remnants, and stellar systems shaped by billions of years of cosmic evolution. As a barred spiral galaxy, roughly 100,000 light-years in diameter, it contains an extraordinary number of stars, each representing a different chapter in the galaxy's long and complex history. By studying the Milky Way's stellar population, how many stars it contains, their types, ages, and spatial distribution, astronomers gain insight into how galaxies form, evolve, and interact with their environments over cosmic time. How many stars are in the Milky Way? One of the most frequently cited and yet most challenging questions in astronomy is deceptively simple. How many stars are in the Milky Way? Current estimates place the number between 100 and 400 billion stars, a range that reflects both observational limitations and genuine uncertainty. Because we live inside the Milky Way rather than observing it from afar, dust clouds, gas, and overlapping stellar populations obscure large portions of the galaxy, making direct counts impossible. Astronomers instead rely on indirect methods. These include measuring the total mass of the galaxy, estimating how much of that mass is contained in stars rather than gas or dark matter, and then extrapolating using known stellar mass distributions. Over time, these techniques have converged toward a middle estimate of around 200 billion stars, which is now commonly quoted in scientific literature and educational sources. Even this figure, however, should be understood as an approximation. As surveys improve and infrared and radio observations penetrate dusty regions of the galaxy, particularly toward the galactic center, estimates may continue to be refined. Stellar ages and the long history of the galaxy. The Sun, at approximately 4.5 billion years old, is often used as a benchmark when discussing stellar ages. Yet many stars in the Milky Way are significantly older. Some formed more than 10 billion years ago, not long after the galaxy itself began to assemble from primordial gas clouds and smaller protogalactic fragments. These ancient stars act as cosmic fossils. Their chemical compositions preserve evidence of the early universe, when heavy elements such as iron, oxygen, and carbon were far rarer than they are today. By studying such stars, astronomers can reconstruct the Milky Way's formative epochs, including periods of intense star formation and ancient mergers with smaller galaxies. At the same time, the Milky Way continues to produce new stars. Star formation is an ongoing process, fueled by vast reservoirs of cold molecular gas in the galactic disk. This means the galaxy hosts stars spanning nearly the entire history of the universe, from some of the oldest known stars to those only a few million years old. Young, hot stars in the galactic disk. The galactic disk is the most visually striking component of the Milky Way, home to its iconic spiral arms. Within these arms reside many of the galaxy's youngest and most massive stars, hot blue stars that burn their nuclear fuel rapidly and shine with extraordinary luminosity. These stars are short-lived on cosmic timescales, often surviving only a few million to tens of millions of years before ending their lives in supernova explosions. Their presence in spiral arms is not accidental. Spiral density waves compress gas clouds as they move through the disk, triggering bursts of star formation. The result is a concentration of young, massive stars tracing out the spiral pattern of the galaxy. Because blue stars emit strongly in ultraviolet and visible light, they dominate the appearance of the Milky Way in many images, despite being vastly outnumbered by smaller, cooler stars. Red dwarfs, the galaxy's quiet majority. Although bright blue stars capture attention, they represent only a tiny fraction of the Milky Way's stellar population. Red dwarf stars, small, cool, and faint, are by far the most numerous type of star in the galaxy. Red dwarfs typically have masses less than half that of the Sun and burn their fuel at an exceptionally slow rate. As a result, their lifespans can extend for hundreds of billions to trillions of years, far longer than the current age of the universe. None of the red dwarfs that have ever formed are expected to have died yet. Individually, red dwarfs are difficult to observe at great distances due to their low brightness. Collectively, however, they dominate the galaxy by sheer numbers and contribute significantly to its total stellar mass. Many of the Sun's nearest stellar neighbors are red dwarfs, underscoring their ubiquity. Their abundance also has profound implications for the search for life beyond Earth. Because red dwarfs are so common and long-lived, they are considered prime targets in the study of exoplanets and habitability, even though their stellar activity poses challenges for life. Star clusters, stellar communities. Stars rarely form in isolation. Most are born within clusters, emerging from the same giant molecular cloud. The Milky Way contains more than 1,000 known open star clusters, which are loose associations of tens to thousands of stars. These clusters are typically found in the galactic disk and are relatively young, often dissolving over hundreds of millions of years as gravitational interactions scatter their members. Open clusters serve as valuable laboratories for studying stellar evolution. Because their stars share a common age and chemical composition, differences in brightness and temperature can be attributed primarily to differences in mass. Famous examples include nearby clusters visible to the naked eye, which have guided astronomical understanding for centuries. In contrast, the galaxy also hosts at least 150 known globular clusters, which are among the oldest structures in the Milky Way. These dense, spherical collections of stars reside primarily in the galactic halo, orbiting far above and below the disk. Globular clusters and Omega Centauri. Globular clusters are remarkable for both their age and density. Each may contain hundreds of thousands or even millions of stars packed into a region only a few dozen light-years across. Their stars are typically more than 10 billion years old, making globular clusters some of the earliest witnesses to the Milky Way's formation. One of the most notable examples is Omega Centauri, the largest and most massive globular cluster associated with the Milky Way. It is so massive and complex that many astronomers believe it may be the remnant core of a dwarf galaxy that was absorbed by the Milky Way long ago. Unlike most globular clusters, Omega Centauri contains multiple stellar populations with different ages and chemical compositions, hinting at a far more intricate history. Globular clusters not only illuminate the early history of the galaxy, but also provide insights into stellar dynamics, gravitational interactions, and the behavior of stars in extreme environments. Black holes, the invisible population. Beyond visible stars and clusters lies a vast population of stellar remnants, including stellar mass black holes. These objects form when massive stars exhaust their nuclear fuel and collapse under their own gravity. While only a relatively small number have been directly detected, usually through interactions with companion stars, astronomers estimate that the Milky Way may contain millions of black holes. Most of these black holes are isolated and invisible, emitting no light of their own. Their presence is inferred statistically based on the number of massive stars that must have formed and died over the galaxy's lifetime. Although they make up only a small fraction of the galaxy's total mass, black holes play a crucial role in shaping stellar environments and enriching the interstellar medium through the supernovae that create them. At the center of the Milky Way lies a supermassive black hole, vastly larger than stellar mass black holes, anchoring the galaxy's core and influencing the motions of nearby stars. Galactic structure. Thin disk, thick disk, bulge, and halo. The Milky Way's stellar population is not randomly distributed. Instead, it is organized into several distinct structural components, each with its own characteristics and history. The thin disk contains most of the galaxy's stars, gas, and dust, including the Sun. It is the primary site of ongoing star formation and hosts stars with a wide range of ages, though it is dominated by relatively younger populations. Above and below the thin disk lies the thick disk, which contains older stars with slightly different chemical compositions. These stars move in more inclined orbits, suggesting a turbulent past, possibly involving mergers or gravitational heating. At the galaxy's center is the bulge, a dense, spheroidal region populated mainly by older stars. The bulge shows evidence of rapid early star formation and complex dynamical processes, including the influence of the central bar structure. Surrounding all of these components is the halo, a vast, sparsely populated region extending far beyond the visible disk. The halo contains ancient stars, globular clusters, and streams of stars left behind by disrupted dwarf galaxies, offering compelling evidence that the Milky Way grew through hierarchical assembly. the architecture of the Milky Way, a galactic system in motion. When we look up at the night sky from Earth, the Milky Way appears as a faint, glowing band stretching across the darkness. To the naked eye, it seems calm and static, but in reality, it is a vast, dynamic system shaped by gravity, motion, and cosmic time. Our galaxy is not a simple collection of stars scattered at random. Instead, it is a carefully structured, multi-layered system composed of distinct components, each with its own physical properties, stellar populations, and role in the galaxy's evolution. The Milky Way is classified as a barred spiral galaxy, a structure shared by many large galaxies in the universe. At its heart lies a dense central bulge surrounded by a rotating disk of stars and gas, threaded by spiral arms and enveloped by a diffuse stellar and gaseous halo that extends far beyond what the eye can see. Understanding this architecture is essential not only for mapping our cosmic neighborhood, but for understanding how galaxies form, evolve, and sustain star formation over billions of years. The central bulge, the galaxy's crowded heart. At the very center of the Milky Way lies the galactic bulge, a dense, spheroidal concentration of stars surrounding the galactic center. This region spans roughly 10,000 light-years and contains an enormous number of stars packed into a relatively small volume of space. Stellar densities here are far higher than in the disk, and stars orbit in complex tilted paths rather than in neat circular orbits. The bulge is dominated by old stars, many of which formed early in the Milky Way's history. These stars tend to be rich in heavier elements compared to the most ancient halo stars, indicating that the bulge experienced intense early star formation, rapidly enriching its gas with material forged in earlier generations of stars. The bulge's stellar population suggests that it formed quickly during a turbulent period when the galaxy was still assembling. At the very center of the bulge lies the galactic center itself, a region obscured from visible light by thick clouds of dust. Infrared and radio observations reveal a bustling environment of stars, gas clouds, and extreme gravitational forces. Anchoring this region is the Milky Way's supermassive black hole, whose immense gravity governs the motions of stars nearby and plays a key role in shaping the central region's dynamics. The galactic disk, a rotating pancake of stars and gas. Surrounding the bulge is the Milky Way's most iconic feature, a flat, rotating disk of stars, gas, and dust. This disk gives the galaxy its familiar spiral shape and contains the majority of its visible matter. When viewed edge-on, the disk resembles a thin pancake stretching tens of thousands of light-years across. The disk rotates around the galactic center, with stars and gas following nearly circular orbits governed by gravity. The Sun itself resides within this disk, about 27,000 light-years from the center, completing one orbit roughly every 225 to 250 million years, a time span often referred to as a galactic year. The disk is not uniform. It contains regions of intense star formation, quiet stellar neighborhoods, massive molecular clouds, and glowing nebulae. This diversity reflects the disk's role as the galaxy's primary engine of ongoing stellar birth and evolution. The thin disk, a surprisingly slim structure. Within the galactic disk, astronomers distinguish between two components, the thin disk and the thick disk. The thin disk is where most of the Milky Way's gas, dust, and young stars reside, and it is astonishingly slim compared to its vast diameter. On average, the thin disk is only about 1,000 light-years thick, a tiny fraction of the galaxy's width. Despite this, it contains a significant portion of the Milky Way's stellar mass. The thin disk's narrow vertical extent reflects the orderly, rotational motion of its stars, which orbit in relatively flat, aligned planes. The thin disk is the primary site of current star formation. Cold molecular gas clouds collapse under gravity to form new stars, many of which will remain in the thin disk for their entire lifetimes. Young stars, star clusters, and nebulae are strongly concentrated here, giving the disk its bright, structured appearance in photographs and surveys. Beyond the disk, the stellar halo. Outside the flattened disk lies a very different component, the stellar halo. This region forms a roughly spherical envelope surrounding the Milky Way, extending far beyond the visible disk, possibly out to hundreds of thousands of light-years from the center. The halo is sparsely populated compared to the disk, but it holds crucial clues to the galaxy's ancient past. Halo stars are typically old and metal-poor, meaning they formed when the universe and the Milky Way contained far fewer heavy elements. Their chemical compositions suggest that many halo stars originated in small protogalaxies that were later absorbed by the growing Milky Way. Unlike disk stars, halo stars move in highly elongated, randomly oriented orbits. This chaotic motion reflects a violent formation history marked by mergers, accretion events, and gravitational disruption. The halo is not smooth. It contains stellar streams, long, faint trails of stars left behind by smaller galaxies that were torn apart as they fell into the Milky Way's gravitational grasp. Globular clusters, ancient relics of the halo. Embedded within the stellar halo are most of the Milky Way's globular clusters, dense spherical collections of stars that rank among the oldest structures in the galaxy. These clusters contain hundreds of thousands, and sometimes millions, of stars tightly bound by gravity. Globular clusters are dominated by very old, metal-poor stars, suggesting that they formed early in the galaxy's history, possibly even before the disk itself was fully assembled. Their spherical shapes and extended orbits through the halo set them apart from the younger, looser open clusters found in the disk. Because all the stars in a globular cluster formed at roughly the same time, these clusters serve as powerful tools for studying stellar evolution and for estimating the age of the Milky Way itself. The galactic bar, a stellar highway through the center. One of the most important discoveries about the Milky Way in recent decades is that it possesses a central bar, an elongated structure of stars stretching across the bulge. This bar spans roughly 25,000 to 30,000 light-years and rotates as a coherent structure, distinct from the surrounding disk. Galactic bars are common in spiral galaxies, and they play a critical role in redistributing mass and angular momentum. In the Milky Way, the bar acts as a gravitational engine, reshaping stellar orbits and influencing the flow of gas throughout the inner galaxy. Stars in the bar follow elongated orbits aligned with the bar's shape, creating a dense, dynamic region that bridges the bulge and the inner disk. The bar's existence helps explain many observed features of the Milky Way's inner structure, including asymmetries in star counts and gas distribution, gas flow and star formation in the central regions. One of the bar's most significant effects is its ability to funnel gas toward the galactic center. As gas clouds orbit within the disk, the bar's gravitational forces torque the gas, causing it to lose angular momentum and spiral inward. This inward flow of gas fuels star formation in the central regions of the galaxy. It also feeds the dense molecular clouds found near the galactic center, creating conditions for massive star clusters to form. In some galaxies, bars can even trigger bursts of star formation or feed active galactic nuclei. In the Milky Way, this process contributes to the complex and energetic environment near the center, where young stars coexist with ancient stellar populations and extreme gravitational forces. Spiral arms, pathways of star birth. Extending outward from the ends of the central bar are the Milky Way's spiral arms, sweeping structures that curve through the disk like cosmic pinwheels. These arms are not rigid structures but regions of enhanced density, waves that move through the disk and compress gas as they pass. The spiral arms contain much of the galaxy's gas and dust, making them prime sites for star formation. As gas clouds are compressed within the arms, they collapse to form new stars, including massive, luminous blue stars that burn hot and fast. These young stars illuminate the arms, making them stand out against the older stellar background. Because massive blue stars have short lifespans, their presence marks recent or ongoing star formation. This is why spiral arms appear rich in bright clusters, nebulae, and glowing regions of ionized gas, the arms as engines of galactic renewal. Spiral arms play a crucial role in sustaining the Milky Way's long-term evolution. By organizing gas into star-forming regions, they regulate when and where new stars are born. This process ensures that star formation is not evenly spread throughout the disk, but concentrated in dynamic, evolving patterns. Over time, stars formed in spiral arms drift away from their birthplaces, dispersing into the disk. New gas flows in, new stars form, and the cycle continues. This constant renewal helps maintain the galaxy's structure over billions of years. The hot gaseous halo, an invisible component. Beyond the stars and cool gas lies another, less visible but equally important component, the hot gaseous halo. This diffuse envelope of ionized gas surrounds the Milky Way and extends far beyond the stellar halo. It is detectable primarily through X-ray observations, as the gas is heated to millions of degrees. The hot halo contains a significant amount of mass, possibly comparable to the mass of all the galaxy's stars combined. It may represent a long-standing mystery in astrophysics, the missing baryons thought to exist in galaxies but not easily observed. This hot gas plays a vital role in galactic evolution. It acts as a reservoir from which cooler gas can condense and fall back into the disk, replenishing the material needed for future star formation. At the same time, energetic events such as supernovae and stellar winds can heat disk gas and expel it into the halo, creating a continuous cycle of inflow and outflow. The spiral structure of the Milky Way, arms, waves, and our place within them. The Milky Way is often imagined as a serene, symmetrical spiral galaxy, its arms gracefully winding outward from a bright central core. In reality, its structure is more complex, dynamic, and subtle than a simple textbook diagram suggests. Because we observe the galaxy from within its disk rather than from a distant vantage point, astronomers must reconstruct its spiral pattern indirectly, using radio waves, infrared light, stellar motions, and the distribution of gas and dust. The result is a picture of a galaxy shaped not by rigid structures, but by waves, motion, and long-term gravitational influences. At the heart of this picture lie the Milky Way's spiral arms, vast regions of enhanced density that organize gas, dust, and stars across tens of thousands of light-years. These arms are not merely decorative features. They are the primary engines of star formation and play a central role in the galaxy's ongoing evolution. Understanding their number, shape, and behavior is essential for understanding both the Milky Way as a whole and the specific environment in which the solar system resides. Major stellar arms, Perseus and Scutum to Centaurus. When astronomers map the distribution of older stars, particularly giant stars that can be seen at great distances, the Milky Way appears to possess at least two major stellar spiral arms. The most prominent of these are commonly identified as the Perseus arm and the Scutum Centaurus arm. These arms stand out because they contain large concentrations of stars that have had time to drift away from their birthplaces. Unlike very young stars, which remain close to the gas clouds that formed them, older stars disperse over time, tracing the long-lived gravitational structure of the galaxy. The Perseus and Scutum Centaurus arms therefore represent the underlying backbone of the Milky Way's spiral pattern. The Scutum Centaurus arm is particularly significant, as it appears to connect directly to one end of the galaxy's central bar and may extend nearly halfway around the galaxy. The Perseus arm lies farther out in the disk and is one of the most easily traced arms from our location, thanks to its rich population of star-forming regions and massive young stars. Together, these two arms dominate the stellar mass distribution within the spiral pattern and suggest that the Milky Way is best described as a galaxy with a strong two-armed stellar structure, overlaid with additional features traced by gas and dust. 4 spiral arms traced by gas and young stars. While older stars highlight 2 dominant arms, a different picture emerges when astronomers observe the galaxy in radio and infrared wavelengths. In these bands, which penetrate interstellar dust and reveal cold gas, the Milky Way shows evidence for 4 main spiral arms. These arms are traced primarily by cold molecular gas clouds, ionized hydrogen regions, young massive blue stars, star-forming complexes, and nebulae. Because radio observations detect emissions from neutral hydrogen and molecules such as carbon monoxide, they provide a detailed map of where star-forming material is concentrated. Infrared observations, meanwhile, reveal warm dust heated by newly formed stars. Together, these techniques show a spiral pattern, richer and more intricate than that traced by older stars alone. The coexistence of 2 dominant stellar arms and 4 gas-rich arms reflects the dynamic nature of spiral structure. Gas responds more strongly to gravitational perturbations than stars do, forming sharper, more numerous features. As a result, the Milky Way's spiral pattern depends on what component is being observed and at what wavelength. The Orion Arm, our local spur. The Sun does not reside in one of the galaxy's major spiral arms. Instead, it is located in a minor spur, often called the Orion Arm or local arm. This structure lies between the Perseus Arm and the Sagittarius Carina Arm and contains a modest but significant concentration of stars and star-forming regions. A spur differs from a major arm in that it is shorter, less massive, and less continuous. Rather than sweeping around the galaxy in a grand arc, the Orion Arm extends for several thousand light-years and appears to branch off from a larger spiral feature. Despite its modest status, the Orion Arm is astrophysically rich. It contains numerous stellar nurseries, including the molecular clouds that gave rise to the Sun and its planetary system. Many of the brightest stars visible from Earth, as well as nearby star-forming regions and nebulae, are part of this local structure. Our position within the Orion Arm has profoundly shaped humanity's view of the galaxy. Because we are embedded in a relatively sparse region rather than a dense major arm, we enjoy clearer views of distant stars and galactic features than we might otherwise have. Distance from the galactic center. The solar system is located approximately 26,000 to 27,000 light-years from the galactic center, placing it about 2/3 of the way out from the center to the edge of the disk. This position situates us well away from the galaxy's most crowded and energetic regions. Closer to the galactic center, stellar densities increase dramatically, and gravitational interactions become more intense. Supernova rates, radiation levels, and dynamical disturbances are all higher in the inner galaxy. Farther out, the disk becomes thinner and less populated, and star formation declines. Our intermediate location offers a relatively stable environment. Over billions of years, this stability may have been an important factor in allowing complex life to develop on Earth. While not free from cosmic hazards, the solar system's position avoids the extremes found closer to the center while remaining within an active star-forming galaxy. Slightly above the galactic mid-plane. In addition to its radial distance, the solar system occupies a position slightly above the mid-plane of the galactic disk. The disk itself is thin, only about 1,000 light-years thick on average, and the Sun sits tens of light-years above its central plane. This offset is small on galactic scales, but it is not insignificant. The Sun oscillates up and down through the disk over tens of millions of years, following a gentle vertical motion driven by the galaxy's gravitational field. This oscillation may periodically expose the solar system to different interstellar environments, including variations in gas density and cosmic radiation. From an observational standpoint, being slightly above the midplane provides clearer lines of sight towards certain regions of the galaxy, reducing the amount of obscuring dust between Earth and distant stars. Density waves, the true nature of spiral arms. One of the most important insights in modern galactic astronomy is that spiral arms are not fixed structures made of the same stars and gas over time. Instead, they are maintained by density waves, long-lived patterns of enhanced gravitational density that move through the disk. In this model, spiral arms function more like traffic jams than rigid objects. As stars and gas orbit the galaxy, they pass into and out of the spiral arms. When gas enters a region of higher density, it slows down slightly, compresses, and becomes more likely to collapse and form new stars. Once it leaves the arm, it continues its orbit while the density wave persists. This mechanism explains several key observations. Spiral arms remain coherent over long periods. Gas is strongly concentrated in arms, while older stars are more spread out. Star formation is enhanced in arms, but not confined permanently to them. Without density waves, spiral arms would quickly wind up and disappear due to differential rotation. The density wave theory provides a framework for understanding how spiral structure can persist for billions of years. Spiral arms as star formation engines. The spiral arms are the primary sites of ongoing star formation in the Milky Way. As gas clouds encounter the increased pressure and density of an arm, they fragment and collapse, giving birth to new generations of stars. Massive blue stars form in abundance within these regions. Because they are short-lived, burning their fuel in just a few million years, they do not travel far from their birthplaces. As a result, their bright light traces the spiral arms clearly, especially in ultraviolet and visible wavelengths. Star formation in spiral arms is not uniform. It occurs in clusters and associations, often triggered by shock fronts and feedback from earlier generations of stars. Supernova explosions and stellar winds inject energy back into the surrounding gas, shaping future star-forming regions and regulating the overall rate of star birth. Dust lanes and obscured starlight. One of the most visually striking features of spiral arms in visible light images is the presence of dark dust lanes. These lanes are composed of dense interstellar dust that absorbs and scatters starlight, creating dark silhouettes against brighter backgrounds. Dust lanes often lie along the inner edges of spiral arms, where gas is compressed most strongly by the density wave. In optical images, they can obscure vast regions of the galaxy, hiding stars and nebulae from view. This obscuration historically limited astronomers' ability to map the Milky Way's structure. Only with the advent of infrared and radio astronomy, capable of seeing through dust, did the true extent and complexity of the spiral arms become apparent. Dust plays a dual role. While it blocks visible light, it is also essential for star formation, providing the raw material and cooling mechanisms necessary for gas clouds to collapse. Inner versus outer spiral structure. The Milky Way's spiral arms are not uniform across the disk. The inner regions of the galaxy exhibit more tightly wound spiral structure than the outer disk. This difference reflects variations in rotational speed, gravitational influence, and gas density. Closer to the galactic center, orbital periods are shorter and gravitational forces are stronger. These conditions favor tightly wrapped spiral patterns. In the outer disk, where orbital speeds are lower and matter is more sparsely distributed, the arms become more open and fragmented. This gradual change in spiral geometry contributes to the galaxy's overall appearance and influences where star formation is most intense. The inner galaxy hosts dense, active star-forming regions, while the outer disk experiences slower, more sporadic star formation. A warped galactic disk. Although often depicted as a perfectly flat disk, the Milky Way's disk is actually slightly warped, bending upward on one side and downward on the other. This warp becomes more pronounced in the outer regions of the disk and is clearly visible in maps of neutral hydrogen gas. The warp is thought to be caused by gravitational interactions with neighboring dwarf galaxies and by the uneven distribution of dark matter surrounding the Milky Way. As smaller galaxies orbit and interact with the Milky Way, their gravitational pull can distort the disk over time. This warp is not static. It evolves slowly as the galaxy responds to ongoing interactions and internal dynamics. The presence of a warp underscores the fact that the Milky Way is not an isolated system, but part of a larger cosmic neighborhood, shaped by continuous interaction and accretion. The galactic center and Sagittarius. A star, the quiet heart of a giant galaxy. From our position inside the Milky Way, the galaxy's center is both one of the most important and most mysterious regions in the sky. Hidden behind dense clouds of dust and gas, the galactic center cannot be studied easily with ordinary telescopes. Yet it is here, deep within the crowded heart of our galaxy, that gravity reigns supreme. Stars race through space at astonishing speeds, and a supermassive black hole quietly anchors the entire system. The galactic center is not simply a point in space. It is a complex environment shaped by extreme conditions, intense gravitational forces, and a long history of energetic events. At its core lies Sagittarius A star, a supermassive black hole with a mass millions of times greater than that of the Sun. Although comparatively quiet today, this object has left unmistakable marks on the structure and evolution of the Milky Way. Understanding the galactic center is essential for understanding the Milky Way as a whole. It is the gravitational and dynamical hub around which the galaxy rotates, a region where astrophysical processes occur at their most intense, and a natural laboratory for testing fundamental theories of gravity and black hole physics. Direction and appearance in the night sky. From Earth, the galactic center lies in the direction of the constellation Sagittarius. When viewed from dark locations in the southern hemisphere, or low on the horizon from northern latitudes, the Milky Way appears brightest and thickest in this direction. The dense star fields, glowing nebulae, and dark dust clouds seen towards Sagittarius mark the line of sight into the galaxy's inner regions. This bright band in the night sky is not a single structure, but the combined light of billions of stars packed along the galactic plane. As our gaze moves towards Sagittarius, we look through progressively denser layers of the Milky Way's disk, culminating in the crowded central bulge. The sheer number of stars in this direction gives the Milky Way its most dramatic appearance. Yet this visual brightness is deceptive. While the Milky Way appears luminous, the true center remains almost completely hidden from view in visible light. Thick clouds of interstellar dust absorb and scatter starlight, creating dark lanes that obscure the deepest regions. To truly see the galactic center, astronomers must turn to wavelengths beyond the visible spectrum. The supermassive black hole at the core. At the very center of the Milky Way lies Sagittarius A star, a supermassive black hole with a mass of approximately 4 million times that of the Sun. Despite its enormous mass, Sagittarius A star is surprisingly compact, confined to a region smaller than the orbit of Mercury around the Sun. Unlike black holes in active galaxies that blaze brightly as they consume vast quantities of matter, Sagittarius A star is relatively quiet. It emits only modest amounts of radiation, indicating that it is currently accreting matter at a very low rate. Nevertheless, its gravitational influence dominates the central region and governs the motion of nearby stars. The existence of Sagittarius A star was not confirmed through direct imaging alone, but through decades of careful observation of stellar motion. By tracking how stars orbit an invisible central object, astronomers were able to infer both the mass and compactness of the black hole with extraordinary precision. Stars in extreme orbits. Some of the most compelling evidence for Sagittarius A star comes from the behavior of stars in its immediate vicinity. Within just a few light years of the galactic center, stars orbit at astonishing speeds, thousands of kilometers per second, far faster than stars elsewhere in the galaxy. These stars follow tight, elongated orbits that bring them extremely close to the black hole before flinging them back outward. One of the best studied examples completes an entire orbit in just over a decade, a blink of an eye on galactic timescales. Such rapid motion is only possible if the central mass is both enormous and confined to a very small volume. By applying the laws of gravity and motion to these stellar orbits, astronomers can calculate the mass of Sagittarius A star with remarkable accuracy. No known object other than a supermassive black hole can explain the observed motions. These measurements provide some of the strongest empirical evidence for the existence of black holes anywhere in the universe. A crowded and energetic environment. The central few light years of the Milky Way are among the most crowded regions in the galaxy. Stars are packed together at densities millions of times greater than those in the Sun's neighborhood. In this environment, gravitational interactions are frequent, and stellar orbits are constantly perturbed. Alongside stars, the region contains dense clouds of gas and dust, some of which are compressed into massive molecular complexes. These clouds are subject to intense tidal forces from the black hole and from the collective gravity of surrounding stars. Despite these harsh conditions, star formation does occur, producing young, massive stars in close proximity to Sagittarius A star. The coexistence of very young stars and an ancient black hole in such an extreme environment presents a challenge to theoretical models. Traditional star formation theories struggle to explain how stars can form so close to a supermassive black hole without being torn apart by tidal forces. This puzzle continues to drive research into alternative star formation mechanisms. Seeing through the dust, radio, and X-ray astronomy. Visible light observations are largely ineffective at probing the galactic center due to heavy dust obscuration. Instead, astronomers rely on radio, infrared, and X-ray observations to study this region in detail. Radio waves pass through dust with little absorption, revealing structures such as gas streams, supernova remnants, and the immediate environment of Sagittarius A star. Infrared observations penetrate much of the dust and allow astronomers to track individual stars orbiting the black hole. These techniques have revolutionized our understanding of the central region. X-ray observations provide insight into the most energetic processes occurring near Sagittarius A star. Hot gas heated to millions of degrees emits X-rays as it spirals toward the black hole or is shocked by stellar winds and supernova explosions. Together, these non-visible wavelengths offer a comprehensive view of a region otherwise hidden from sight. Evidence of past energetic outbursts. Although Sagittarius, a star, is relatively quiet today, the galactic center bears unmistakable signs of past energetic activity. One of the most dramatic examples is the presence of enormous structures known as Fermi bubbles, vast lobes of high-energy radiation extending tens of thousands of light-years above and below the galactic plane. These bubbles are thought to have formed during a period of intense activity in the Milky Way's nucleus, possibly triggered by a burst of gas accretion onto Sagittarius A star, or by a concentrated episode of star formation and supernova explosions near the center. The energy required to create such structures is immense, indicating that the galactic center was far more active in the past. The Fermi bubbles demonstrate that even a galaxy with a relatively quiet nucleus today can experience dramatic episodes of energy release. They also highlight the role that supermassive black holes can play in influencing their host galaxies on large scales. A quiet nucleus by galactic standards. Compared to the blazing cores of some galaxies, known as active galactic nuclei, the Milky Way's nucleus is remarkably subdued. In active galaxies, supermassive black holes accrete matter at high rates, producing intense radiation, powerful jets, and luminous emission across the electromagnetic spectrum. Sagittarius A star, by contrast, accretes matter very inefficiently. The surrounding gas is hot and diffuse, and much of it is likely expelled by winds before it can reach the event horizon. As a result, the black hole emits only a tiny fraction of the energy it would produce if it were actively feeding. This relative calm makes the Milky Way a valuable comparison point. By studying a quiescent supermassive black hole up close, astronomers can better understand the full range of black hole behavior, from dormant to violently active, and the factors that determine where a given galaxy falls on that spectrum. Occasional X-ray flares. Despite its overall quiet state, Sagittarius A star is not entirely inactive. Astronomers have observed occasional X-ray and infrared flares originating from the region near the black hole. These flares occur when small amounts of gas or dust fall inward, heating up and emitting bursts of radiation before disappearing beyond the event horizon. These flares are brief, lasting from minutes to hours, but they provide valuable insight into the physics of accretion and the behavior of matter in extreme gravitational fields. By monitoring these events, astronomers can probe conditions just outside the black hole and test predictions of general relativity. The flares also serve as a reminder that Sagittarius A star remains a dynamic object capable of responding quickly to changes in its environment, even while remaining relatively faint on average. The galactic center as a gravitational anchor. Beyond its immediate environment, Sagittarius A star plays a fundamental role in the structure of the Milky Way. Its mass contributes to the gravitational potential that shapes stellar orbits in the central bulge and influences the dynamics of the inner galaxy. While the black hole does not directly control the motion of stars far from the center, its presence is essential for maintaining the stability of the nuclear region. It also provides a reference point for defining the galaxy's coordinate system and for understanding the rotation and mass distribution of the Milky Way as a whole. The galactic center thus serves as both a physical and conceptual anchor, a point around which the galaxy's vast spiral disk revolves. A laboratory for extreme physics. The proximity of the galactic center makes it one of the best natural laboratories for studying extreme astrophysical phenomena. Nowhere else can astronomers observe the environment around a supermassive black hole with such precision. Studies of stellar orbits near Sagittarius A star have provided some of the most stringent tests of Einstein's theory of general relativity. Observations of gas dynamics, magnetic fields, and high-energy radiation probe conditions that cannot be replicated on Earth or in laboratories. As observational technology advances, particularly in the realms of infrared interferometry, X-ray astronomy, and radio imaging, the galactic center continues to yield new insights into the fundamental laws governing matter, energy, and gravity. A calm present, a violent past, an uncertain future. The galactic center today is calm compared to its more active counterparts in other galaxies. Yet the evidence of past outbursts and ongoing low-level activity suggests that this tranquility is not permanent. Over cosmic timescales, changes in gas supply, stellar winds, or interactions with infalling material could once again awaken Sagittarius A star. Understanding these cycles of activity is crucial for placing the Milky Way in its broader cosmic context. Our galaxy is not unique. It is one of hundreds of billions of galaxies in the observable universe, each with its own central black hole and evolutionary history. By studying our own galactic center in detail, astronomers gain insight into the life cycles of galaxies everywhere, motion, rotation, and orbits in the Milky Way. The night sky often gives the impression of stillness. Stars appear fixed in place, constellations seem unchanged across human lifetimes, and the Milky Way itself looks like a quiet, luminous band stretched across the heavens. Yet this apparent calm is an illusion. In reality, everything within the Milky Way is in constant motion. Stars, gas, dust, and dark matter are all engaged in an intricate gravitational dance, orbiting the galaxy's center, oscillating through its disk, and responding to forces that operate across tens of thousands of light years. Understanding motion within the Milky Way is fundamental to understanding what a galaxy truly is. A galaxy is not a static structure frozen in space, but a dynamic system defined by rotation, orbital paths, and long-term gravitational equilibrium. From the Sun's slow circuit around the galactic center to the random motions of stars in the bulge and halo, these movements encode the galaxy's mass distribution, its formation history, and the invisible presence of dark matter. Galactic rotation, a system in motion. At the largest scale, the Milky Way rotates as a single gravitational system around its central region. This rotation is not rigid, like a solid disk turning on an axle, but differential, meaning that material at different distances from the center moves at different angular speeds. The bulk of this rotation is carried by the galaxy's disk, which contains most of its stars, gas, and dust. Everything within the disk orbits the galactic center under the influence of gravity. This motion is what maintains the galaxy's flattened spiral structure and prevents it from collapsing inward. The existence of organized rotation was first inferred through measurements of stellar velocities and gas motions. Over time, increasingly precise observations revealed that the Milky Way behaves like a massive rotating system, whose motion is governed by a combination of visible matter and a much larger, unseen mass component. Orbital speeds in the disk. Stars, gas, and dust in the galactic disk orbit the galactic center at an average speed of about 220 kilometers per second. This is an extraordinary velocity by everyday standards, fast enough to travel from Earth to the Moon in under half an hour. Yet it is typical for stars in spiral galaxies. This orbital speed is remarkably consistent across much of the disk. Whether a star lies somewhat closer to the center or farther out, its orbital velocity remains close to this value. This uniformity is one of the most important clues to the Milky Way's underlying mass structure. Gas clouds, atomic hydrogen, molecular clouds, and dust grains all participate in this rotation. Because gas emits radiation at specific radio wavelengths, particularly the 21 centimeter line of hydrogen, astronomers can track its motion with exceptional precision. These measurements form the backbone of our understanding of galactic rotation. The Sun's galactic orbit. The Sun is not stationary within the Milky Way. It follows a nearly circular orbit around the galactic center at roughly the same speed as neighboring stars, about 220 kilometers per second. At this pace, the Sun completes one full orbit every 225 to 250 million years, a period commonly referred to as a galactic year. This means that since the Sun formed about 4.5 billion years ago, it has completed roughly 18 to 20 full revolutions around the galaxy. During each of these journeys, the solar system has passed through different spiral environments, encountered varying interstellar conditions, and experienced subtle changes in gravitational surroundings. A single galactic year is so long that it dwarfs human timescales. When the Sun last occupied its current galactic position, dinosaurs were just beginning to appear on Earth. Entire epochs of biological evolution unfold during just a fraction of a galactic orbit. A full circle through the disk. During one galactic year, the Sun travels one complete circuit through the disk, tracing a nearly circular path around the center. This orbit lies within the thin disk, the region where most star formation occurs and where stellar motions are highly ordered. The Sun's orbit is not perfectly circular. It has a slight eccentricity, meaning its distance from the center varies modestly over time. However, this deviation is small compared to the more elliptical orbits seen in other galactic components, such as the bulge or halo. As the Sun moves, it remains embedded within the same general stellar population, surrounded by stars of similar age and composition. This stability is one reason the solar system has enjoyed a relatively calm, dynamical history, free from frequent close encounters with other stars or strong gravitational disturbances. Vertical motion through the galactic plane. In addition to orbiting the galactic center, the solar system undergoes a slower vertical motion relative to the galactic disk. Rather than remaining fixed within the disk's mid-plane, the Sun oscillates up and down through the galactic plane. This vertical oscillation is driven by the collective gravitational pull of the disk's mass. As the Sun moves slightly above the plane, gravity pulls it back downward. Once it passes through the plane, the same force eventually slows and reverses its motion. The result is a gentle bobbing motion superimposed on the Sun's circular orbit. The amplitude of this oscillation is modest, on the order of tens of light years, but it is significant enough to expose the solar system to slightly different galactic environments over time. Frequency of vertical oscillation. The Sun completes approximately 2.7 vertical oscillations for every orbit around the galactic center. In other words, during one galactic year, the solar system passes through the mid-plane of the disk multiple times. Each oscillation takes on the order of 70 to 90 million years. This rhythm has intrigued scientists because it roughly coincides with certain long-term patterns observed in Earth's geological and biological records. While no definitive causal links have been established, the idea that galactic motion could influence conditions in the solar system remains an active area of research. Regardless of any terrestrial implications, the Sun's vertical motion is a natural consequence of living within a massive, flattened gravitational system. Motion of the Milky Way through the universe. The Milky Way itself is not stationary in the cosmos. As part of the expanding universe and a member of a local group of galaxies, it moves through space at a velocity of approximately 552 kilometers per second relative to the cosmic microwave background. The cosmic microwave background, CMB, provides a reference frame for large-scale cosmic motion. It represents the afterglow of the Big Bang and appears nearly uniform in all directions. Small variations in its temperature reveal the motion of galaxies relative to this primordial radiation field. The Milky Way's motion reflects the gravitational influence of nearby structures, including neighboring galaxies and larger cosmic filaments. This velocity does not affect the internal motions of stars within the galaxy, but it situates the Milky Way within the broader flow of matter in the universe. Ordered motion in the disk. One of the defining features of the galactic disk is the high degree of order in stellar orbits. Disk stars move on nearly circular paths confined close to the mid-plane and share a common direction of rotation. This ordered motion reflects the disk's formation history. As gas cooled and settled into a rotating plane early in the galaxy's life, angular momentum was conserved, producing a flattened structure with coherent rotation. Stars formed from this gas inherited its orderly motion. Because of this regularity, encounters between disk stars are rare and gravitational perturbations are relatively mild. This stability allows planetary systems to survive for billions of years without being disrupted by close stellar flybys. Motion in the galactic bulge. In stark contrast to the disk, stars in the galactic bulge exhibit much more random and elliptical orbits. Rather than moving in neat circles, bulge stars follow paths that plunge inward and outward, often at steep angles relative to the disk. This chaotic motion reflects the bulge's origin. The bulge likely formed early in the Milky Way's history through rapid star formation, mergers, and gravitational instabilities. These processes scrambled stellar orbits, producing a spheroidal distribution rather than a flat disk. Although bulge stars still orbit the galactic center overall, their individual motions are less predictable and less aligned. This randomness results in higher stellar velocities near the center and contributes to the dense, dynamic environment surrounding the galaxy's nucleus. Halo orbits, long and inclined. Beyond the disk and bulge lies the stellar halo, whose stars move in some of the most extreme orbits in the galaxy. Halo stars often travel on long, highly inclined and elongated paths, taking them far above and below the disk and deep into the galaxy's outskirts. Many halo stars spend most of their time far from the galactic plane, only briefly passing through the inner regions. Their orbits are not aligned with the disk's rotation and can even be retrograde, moving opposite to the disk's general motion. This behavior reflects the halo's origin as a repository of ancient stars and the remnants of smaller galaxies absorbed by the Milky Way. Each merger event left behind stars on distinctive orbits, contributing to the halo's kinematic diversity. Orbital energy and galactic memory. The motions of stars within the Milky Way preserve a record of the galaxy's past. Orbital shapes, inclinations, and velocities act as fossil evidence of earlier events such as mergers, accretion, and gravitational disturbances. Disk stars tell the story of gradual, ordered evolution. Bulge stars reflect violent early assembly. Halo stars reveal a history of cosmic cannibalism in which the Milky Way grew by consuming smaller systems. By studying stellar motions, an approach known as galactic archaeology, astronomers can reconstruct how the Milky Way formed and evolved over billions of years. The rotation curve problem. One of the most profound discoveries in galactic astronomy comes from measuring how orbital speed varies with distance from the galactic center. According to classical Newtonian expectations, stars farther from the center should orbit more slowly, just as planets farther from the Sun move more slowly. However, observations show that the Milky Way's rotation curve remains flat at large radii. Beyond the inner regions, orbital speeds do not decline significantly with distance. Stars tens of thousands of light-years from the center move at nearly the same speed as those much closer in. This behavior cannot be explained by the gravitational influence of visible matter alone. The role of dark matter. The flat rotation curve provides compelling evidence for the existence of dark matter, an invisible form of matter that does not emit or absorb light but exerts gravitational influence. Dark matter is thought to form a massive, roughly spherical halo surrounding the Milky Way, extending far beyond the visible disk. This halo contains several times more mass than all the galaxy's stars and gas combined. The gravitational pull of dark matter keeps orbital speeds high even at large distances from the center. Without it, the outer regions of the galaxy would not remain gravitationally bound and would drift away into intergalactic space. Dark matter's presence is inferred not only from rotation curves, but also from gravitational lensing, cosmic structure formation, and the motions of galaxies in clusters. Within the Milky Way, its influence is most clearly seen in the persistence of high orbital velocities across the disk. Stability through motion. The motions within the Milky Way are not chaotic on large scales. Despite the complexity of individual orbits, the galaxy as a whole is remarkably stable. Its rotation, supported by angular momentum and dark matter, has persisted for billions of years. This stability allows spiral arms to form, star formation to continue, and planetary systems to endure. It also means that dramatic changes in galactic structure occur only over immense timescales. The galaxy's motions are thus both dynamic and enduring, a balance between movement and long-term equilibrium. A moving home in a moving universe. Every moment, the Earth is carried through space by multiple overlapping motions. Rotation on its axis, orbit around the Sun, the Sun's orbit around the galactic center, the Milky Way's motion through the local group, and the expansion of the universe itself. These motions are not abstract concepts. They are the physical reality of our existence. The Sun's steady journey through the Milky Way has shaped the environment in which life evolved and will continue long after humanity's time has passed. Understanding motion, rotation, and orbits in the Milky Way transforms the galaxy from a static image into a living system, a vast rotating structure whose invisible forces govern the paths of billions of stars, including our own. Dark matter and the invisible architecture of the galaxy. When we look up at the night sky, everything we see, stars, nebulae, glowing gas clouds, feels vast and overwhelming. The Milky Way appears immense, a luminous system containing hundreds of billions of stars bound together by gravity. Yet modern astrophysics has revealed a deeply counterintuitive truth. Almost everything we can see makes up only a small fraction of what is actually there. The majority of the mass in the Milky Way is invisible. It does not shine, glow, absorb, or reflect light. It does not emit radio waves, infrared radiation, X-rays, or gamma rays. And yet without it, the Milky Way could not exist in its present form. This hidden component, dark matter, dominates the galaxy's mass, shapes its structure, governs the motion of its stars, and extends far beyond its visible boundaries. Dark matter is one of the most profound and enduring mysteries in modern science. It connects the smallest galactic motions to the largest cosmic structures and challenges our understanding of matter, gravity, and the fundamental composition of the universe. The missing mass problem. Early astronomical models of the Milky Way assumed that its mass was primarily contained in its visible components, stars, gas, and dust. By estimating the brightness of stars and applying known relationships between luminosity and mass, astronomers attempted to calculate how much matter the galaxy contained. However, when stellar motions were measured with increasing precision, a troubling discrepancy emerged. Stars were moving too fast to be held in orbit by the gravitational pull of visible matter alone. According to classical physics, much of the galaxy should have flown apart. This problem was not unique to the Milky Way. Similar discrepancies were found in other spiral galaxies, galaxy clusters, and eventually in the large-scale structure of the universe itself. Everywhere astronomers looked, gravity appeared stronger than could be explained by visible matter alone. The conclusion became unavoidable. Most of the galaxy's mass is invisible. Visible matter, only the tip of the iceberg. All the stars, planets, gas clouds, dust and nebulae in the Milky Way together account for only a minor fraction of its total mass. Even when every detectable form of ordinary matter is included, hydrogen gas, molecular clouds, stellar remnants, and interstellar dust, the total still falls far short of what is required to explain the galaxy's gravitational behavior. This ordinary matter, known as baryonic matter, makes up everything we are familiar with in everyday life. Yet on galactic scales, baryons are vastly outnumbered by something else. Estimates suggest that visible matter accounts for only about 10 to 20% of the Milky Way's total mass. The remaining 80 to 90% is attributed to dark matter. This imbalance fundamentally changes how astronomers think about galaxies. Rather than being collections of stars with some extra mass attached, galaxies are now understood as dark matter structures that happen to contain stars. The dark matter halo. The dominant repository of dark matter in the Milky Way is an enormous, roughly spherical structure known as the dark matter halo. This halo surrounds the visible galaxy, enveloping the disk, bulge, and stellar halo, and extending far beyond them into intergalactic space. Unlike the galaxy's luminous disk, which is thin, flat, and sharply defined, the dark matter halo is diffuse and extended. Its density decreases gradually with distance from the center without a clear outer edge. Estimates suggest that the halo may extend several 100,000 light-years from the galactic center, possibly reaching distances comparable to the separation between the Milky Way and its neighboring galaxies. The halo contains the majority of the galaxy's mass, and it is this mass that dominates the Milky Way's gravitational potential. Every star orbiting the galaxy, including the Sun, moves primarily in response to the gravitational influence of the dark matter halo rather than the visible disk alone. The flat rotation curve, a key clue. One of the strongest pieces of evidence for dark matter comes from the Milky Way's rotation curve, a plot showing how orbital speed varies with distance from the galactic center. If the galaxy's mass were concentrated mainly in its visible components, orbital speeds would behave much like planetary orbits in the solar system. Stars farther from the center would move more slowly. Instead, observations reveal something very different. Beyond the inner regions of the Milky Way, orbital speeds remain nearly constant with increasing distance. Stars, tens of thousands of light-years from the center, orbit at almost the same speed as stars much closer in. This behavior is known as a flat rotation curve. Such a curve is impossible to explain without invoking a large amount of unseen mass distributed throughout the galaxy. The flat rotation curve implies that mass continues to increase with distance, even where there is little visible matter. Dark matter provides the simplest and most consistent explanation, shaping the galaxy's gravitational potential. Dark matter does more than merely add extra mass. It shapes the entire gravitational framework of the Milky Way. The orbits of stars, gas clouds, and satellite galaxies are all determined by the combined gravitational influence of visible matter and the dark matter halo. The smooth, extended nature of the halo helps stabilize the galaxy's disk, preventing it from fragmenting or collapsing. It influences the formation and persistence of spiral arms and affects how gas flows within the galaxy. Even the long-term survival of the Milky Way as a coherent structure depends on dark matter. Without the halo's gravitational binding, the outer regions of the galaxy would be vulnerable to disruption by nearby galaxies and cosmic tides. In this sense, dark matter acts as the invisible scaffolding upon which the visible galaxy is built. Extent of the halo. While the luminous disk of the Milky Way spans roughly 100,000 light-years, the dark matter halo extends much farther. Measurements of stellar motions, satellite galaxy orbits, and high-velocity gas clouds suggest that the halo reaches out to at least 300,000 light-years and possibly farther. This means that much of the Milky Way's mass lies well beyond the regions where stars are found. The galaxy's true size, defined by its gravitational influence, is therefore far larger than its visible appearance suggests. The halo's vast extent also means that the Milky Way's gravitational reach overlaps with that of neighboring galaxies, shaping interactions within the local group. An unknown substance. Despite decades of study, the true nature of dark matter remains unknown. This mystery stands as one of the greatest open problems in astrophysics and fundamental physics. Dark matter does not interact with electromagnetic radiation, which is why it is invisible to telescopes. It does not emit, absorb, or reflect light. It appears to interact with ordinary matter almost exclusively through gravity, and possibly through extremely weak, as yet undetected forces. Numerous candidates have been proposed, ranging from new elementary particles to exotic states of matter. Some theories suggest dark matter consists of massive, slow-moving particles formed in the early universe. Others propose more radical modifications to our understanding of gravity itself. So far, no direct detection experiment has conclusively identified dark matter particles. Every piece of evidence for dark matter remains indirect, inferred from its gravitational effects. Influence on satellite galaxies. The Milky Way is accompanied by dozens of smaller satellite galaxies, many of which orbit deep within its dark matter halo. The motions of these satellites provide valuable clues about the halo's mass and structure. Some satellite galaxies move at surprisingly high speeds, requiring a large amount of unseen mass to keep them gravitationally bound. Others show signs of tidal distortion, stretched and torn by the Milky Way's gravitational field. These interactions are governed largely by the dark matter halo. Its shape, mass distribution, and extent determine how satellite galaxies move, how long they survive, and how they are eventually disrupted. In this way, dark matter plays a central role in the ongoing growth and evolution of the Milky Way through the accretion of smaller systems. Gravitational lensing as a probe. Although dark matter cannot be seen directly, it can reveal itself through gravitational lensing, the bending of light caused by mass. According to general relativity, mass warps spacetime, causing light from background objects to curve as it passes nearby. Even invisible mass can produce this effect. In principle, careful measurements of lensing can be used to map the distribution of dark matter. For the Milky Way, gravitational lensing is more challenging to observe than in distant galaxy clusters, but it still provides potential constraints. Subtle distortions in the apparent positions and brightness of background stars can hint at the presence and clumping of dark matter within the halo. Future surveys and instruments may make it possible to use lensing more effectively to probe the Milky Way's dark matter distribution. Dark matter to visible matter ratio. Estimates of the Milky Way's total mass suggest that dark matter outweighs visible matter by several times, typically quoted as a ratio of roughly 5:1, though exact values vary depending on assumptions and measurement techniques. This means that for every kilogram of stars, gas, and dust, there are several kilograms of dark matter exerting gravitational influence. This ratio is not unique to the Milky Way. Many galaxies show similar proportions, suggesting that dark matter is a fundamental component of galaxy formation rather than a peculiar feature of our own system. Detection only through gravity. A defining feature of dark matter is that it has never been detected through direct electromagnetic signals. Every inference about its existence comes from gravity, orbital motions, rotation curves, lensing effects, and cosmic structure formation. This makes dark matter fundamentally different from any form of matter previously studied in laboratories. It challenges experimental physics to devise new methods of detection and challenges theoretical physics to integrate dark matter into a coherent framework of fundamental particles and forces. The search for dark matter extends beyond astronomy into particle physics, cosmology, and experimental underground detectors, all working toward the same goal: identifying the substance that dominates the mass of the universe. Dark matter and galactic history. Dark matter did not merely shape the present-day Milky Way, it shaped its entire history. In the early universe, dark matter began to clump under gravity before ordinary matter could cool and collapse. These dark matter concentrations acted as seeds around which gas collected, eventually forming the first stars and galaxies. The Milky Way likely formed within one such dark matter halo, growing through mergers and accretion over billions of years. The halo preserved the memory of these events even as stars formed and evolved within it. In this sense, dark matter is the architect of galactic structure, determining where galaxies form, how massive they become, and how they interact. Environment, satellites, and the future of the Milky Way. Galaxies do not exist in isolation. Although they may appear as solitary islands of stars scattered across a dark cosmic ocean, every galaxy is embedded within a larger environment shaped by gravity, motion, and cosmic history. The Milky Way is no exception. Our galaxy is part of a hierarchy of structures, satellite systems, galaxy groups, and superclusters that influence its past, present, and future. From the small dwarf galaxies that orbit close to us, to the vast cosmic web that governs the motion of entire galaxy groups, the Milky Way is deeply interconnected with its surroundings. Understanding the Milky Way's environment is essential for understanding how it formed, how it continues to evolve, and what ultimately awaits it billions of years from now. Its satellites preserve the fossil record of galactic growth. Its place within the local group reveals how galaxies interact on moderate scales, and its eventual collision with a neighboring giant galaxy demonstrates that even large, majestic systems like the Milky Way are temporary arrangements in an ever-changing universe. The local group, our galactic neighborhood. The Milky Way belongs to a small association of galaxies known as the local group. This group is bound together by gravity and spans a region roughly 10 million light-years across. Compared to rich galaxy clusters that can contain thousands of members, the local group is relatively modest in size. Nevertheless, it represents a complete miniature ecosystem of galactic evolution. The local group contains more than 30 known member galaxies, ranging from massive spirals to tiny dwarf systems barely visible even with modern telescopes. These galaxies are not randomly scattered. They are gravitationally bound and move in complex orbits around the group's collective center of mass. The local group formed from primordial density fluctuations in the early universe. As dark matter clumped together, ordinary matter followed, cooling and condensing into the first galaxies. Over billions of years, these galaxies interacted, merged, and settled into the configuration we observe today. Two giants of the group, Milky Way and Andromeda. Dominating the local group are two massive spiral galaxies, the Milky Way and the Andromeda galaxy. Together, they contain the majority of the group's total mass and exert the strongest gravitational influence on smaller members. The Milky Way and Andromeda are roughly comparable in size and mass, though Andromeda may be slightly more massive. Each hosts hundreds of billions of stars, extensive dark matter halos, and large satellite systems. These two galaxies effectively form a binary system, slowly moving toward each other under their mutual gravitational attraction. Most of the remaining galaxies in the local group are either satellites of one of these two giants or move within the gravitational field dominated by them. In this sense, the Milky Way and Andromeda act as the structural anchors of the entire group. The wider cosmic context, the Virgo supercluster and local sheet. The local group itself is not an isolated structure. It is embedded within a much larger arrangement of galaxies often referred to as the Virgo supercluster, or more precisely, the local sheet region. This larger structure contains thousands of galaxies organized along filaments and sheets shaped by the distribution of dark matter on vast scales. On these scales, gravity organizes matter into a cosmic web, with dense clusters at the intersections of filaments and relatively empty voids in between. The local group resides in a comparatively quiet region of this web, far from the dense core of the Virgo cluster itself, but still influenced by its gravitational pull. The motion of the local group through space, along with its eventual interactions with other structures, is shaped by this larger environment. Even on scales far beyond individual galaxies, gravity continues to sculpt the universe. A system rich in satellites. Orbiting the Milky Way is a diverse population of satellite galaxies. Current observations suggest that the Milky Way has at least about 60 known satellites, though this number continues to grow as deeper surveys reveal fainter and more diffuse objects. These satellites range from relatively substantial dwarf galaxies to tiny systems containing only a few thousand stars. Most are dominated by dark matter and contain very little gas, making them faint and difficult to detect. Satellite galaxies are not merely companions, they are relics of the Milky Way's formation. According to modern theories of galaxy formation, large galaxies grow by accreting smaller ones. Many of the satellites we see today are survivors of this process, systems that have not yet been fully absorbed. The Magellanic Clouds, the largest satellites. The most prominent satellite galaxies of the Milky Way are the Large Magellanic Cloud and the Small Magellanic Cloud. These two irregular dwarf galaxies are easily visible to the naked eye from the southern hemisphere and have been known to human observers for centuries. Unlike many other satellites, the Magellanic Clouds are gas-rich and actively forming stars. Their irregular shapes reflect a turbulent history shaped by gravitational interactions with both the Milky Way and each other. These galaxies are connected by a vast stream of gas known as the Magellanic Stream, which stretches tens of thousands of light-years across the sky. This stream provides direct evidence of tidal forces at work and illustrates how satellite galaxies lose material as they orbit a massive host. Irregular dwarf galaxies in motion. The Magellanic Clouds are classified as irregular dwarf galaxies, lacking the orderly spiral structure seen in larger systems. Their shapes are distorted by gravitational interactions, and their internal motions are chaotic compared to those of the Milky Way's disk. These galaxies may be relatively recent arrivals to the Milky Way's environment. Some evidence suggests they are on their first or second close pass around the Milky Way, rather than long-term satellites. If so, they represent an ongoing phase of galactic growth, rather than a relic of ancient history. Over time, continued interaction will likely strip gas from the Magellanic Clouds and eventually merge them into the Milky Way, adding their stars to the galactic halo and disk. The smallest satellites, ultra-faint dwarfs. Beyond the Magellanic Clouds lie dozens of much smaller satellites, some of which are among the faintest galaxies known. Examples include systems such as the Carina Dwarf and Leo Dwarf galaxies. These ultra-faint dwarfs can be only a few hundred light-years across, making them smaller than many globular star clusters. Despite their diminutive size, they are classified as galaxies because they are dominated by dark matter rather than by stellar mass alone. In some cases, these galaxies contain only a few thousand stars, all of which are old and metal-poor. They appear to have formed stars early in cosmic history and then lost their gas, shutting down further star formation. Dark matter laboratories. The smallest satellite galaxies are of enormous scientific importance. Because they contain very little visible matter but are strongly influenced by gravity, They provide some of the strongest evidence for dark matter on small scales. Measurements of stellar velocities within these dwarfs reveal that they are held together by far more mass than their stars can account for. In some cases, dark matter outweighs visible matter by factors of hundreds or more. These galaxies therefore act as natural laboratories for testing theories of dark matter and galaxy formation. Their abundance, distribution, and internal structure place strong constraints on cosmological models, tidal disruption, and stellar streams. Not all satellite galaxies survive intact. As they orbit the Milky Way, many experience tidal disruption, a gradual tearing apart caused by the galaxy's gravitational field. As stars are stripped from a satellite, they spread out along the satellite's orbit, forming elongated structures known as stellar streams. These streams wrap around the Milky Way, tracing the paths of former galaxies that are now being absorbed. The stellar halo of the Milky Way is laced with such streams, each representing a past or ongoing merger event. By mapping these streams, astronomers can reconstruct the galaxy's accretion history in remarkable detail. Galactic cannibalism as a growth mechanism. The process of absorbing smaller galaxies is often referred to as galactic cannibalism, though it is better understood as a natural consequence of hierarchical structure formation. Over billions of years, the Milky Way has grown by incorporating the stars, gas, and dark matter of smaller systems. This process is ongoing and will continue into the future. Each merger subtly alters the Milky Way's structure, thickening its disk, enriching its halo, and adding complexity to its stellar populations. The galaxy we see today is the cumulative result of countless such events. The Milky Way and Andromeda on a collision course. Perhaps the most dramatic aspect of the Milky Way's future environment is its relationship with Andromeda. Precise measurements of Andromeda's motion show that it is moving toward the Milky Way at several hundred kilometers per second. In approximately 4 to 5 billion years, the two galaxies are expected to collide and eventually merge. This event will mark one of the most significant transformations in the Milky Way's history. Despite the word collision, individual stars are extremely unlikely to collide directly, as the distances between stars are vast. Instead, the galaxy's gravitational fields will interact, distorting their shapes, triggering bursts of star formation and redistributing stars across new orbits. Stages of the future merger. The merger between the Milky Way and Andromeda will likely unfold over several billion years. Initial close passes will produce tidal tails and warped disks. Subsequent encounters will further disrupt the galaxy's structures until they finally coalesce into a single system. The end result is expected to be a large elliptical or lenticular galaxy, sometimes informally called Milky Way. Its spiral arms will be destroyed, replaced by a more spheroidal distribution of stars. By the time this merger occurs, the Sun will be nearing the end of its life, having exhausted much of its nuclear fuel. If Earth still exists in any recognizable form, the night sky will be profoundly different, dominated by the distorted glow of the merging galaxies. The fate of satellite galaxies. During the merger, the satellite systems of both galaxies will be reshuffled. Some satellites will be absorbed early, Others may be flung into distant orbits, and a few may survive as independent companions to the merged galaxy. The dark matter halos of the Milky Way and Andromeda will merge first, guiding the overall dynamics of the event. The visible galaxies will follow, responding to the invisible gravitational framework. This process illustrates the central role of dark matter in shaping not only galaxies, but their futures. The long-term cosmic perspective. On even longer timescales, the local group itself will continue to evolve. Some galaxies may drift away, while others may merge into the central remnant. The expansion of the universe will eventually isolate the local group from more distant structures, as cosmic acceleration pulls them beyond our observable horizon. In the far future, the merged Milky Way Andromeda system may be one of the last galaxies visible to its inhabitants, surrounded by darkness as the universe expands ever faster. Observations and perspective. Understanding the Milky Way from the inside. Humanity's understanding of the universe has always been shaped by perspective. From Earth, the sun appears to move across the sky. Only later did we learn that it is Earth that moves. In the same way, our understanding of the Milky Way is profoundly influenced and limited by the fact that we are embedded deep within it. We do not observe our galaxy from a distant vantage point, but from inside its disk, surrounded by stars, gas, and dust. This internal perspective makes the Milky Way both intimately familiar and extraordinarily difficult to comprehend. Unlike distant galaxies, which can be photographed in their entirety, the Milky Way must be reconstructed piece by piece. Astronomers rely on indirect methods, multi-wavelength observations, and massive data sets to infer its structure, history, and dynamics. Even after centuries of observation and decades of space-based astronomy, many of the galaxy's most fundamental properties remain subjects of active research. The story of how we observe and understand the Milky Way is therefore not just a story of the galaxy itself, but of human ingenuity, of learning how to see the unseen, how to interpret motion and light, and how to build a coherent picture of a system we cannot step outside of. The challenge of an internal viewpoint. Mapping the Milky Way presents a challenge unlike that of studying any other galaxy. Because we reside within the galactic disk, our view is constrained by distance, perspective, and obstruction. Dense clouds of interstellar dust lie between us and large portions of the galaxy, absorbing and scattering visible light. Entire regions, especially toward the center, are effectively opaque at optical wavelengths. This obscuration produces dramatic visual effects. The Milky Way appears as a bright band across the sky, but that brightness is uneven, interrupted by dark lanes and rifts. These are not gaps in stars, but dust clouds blocking the light of billions of distant suns. What we see is therefore not a direct map of stellar distribution, but a filtered projection shaped by intervening material. Perspective compounds the problem. From inside the disk, distance is difficult to judge. Stars at vastly different distances can appear side by side, and faint nearby stars can be confused with distant luminous ones. Without accurate distance measurements, it is impossible to distinguish structure from coincidence. For much of history, these limitations led to incorrect conclusions. Early astronomers debated whether the Milky Way was the entire universe. a disk of stars centered on the Sun, or something else entirely. Only gradually did it become clear that the Milky Way is a vast galaxy, and that the Sun occupies no special central position within it. Dust as an obstacle and a clue. Interstellar dust is both an obstacle to observation and a key component of the galaxy's ecology. Composed of tiny grains of carbon and silicate-based material, dust absorbs visible light and re-emits energy at longer wavelengths. In optical images, dust appears as dark silhouettes. In infrared, it glows. Dust obscuration is strongest along the galactic plane, where gas and dust are concentrated. Toward the galactic center, extinction becomes so severe that visible light telescopes are effectively blind. Even relatively nearby star-forming regions can be hidden behind dense dust clouds. Yet dust also tells a story. Its distribution traces spiral arms, star-forming regions, and large-scale structure. The dark lanes visible to the naked eye under pristine skies are markers of where the galaxy is actively recycling material into new generations of stars. Understanding the Milky Way requires learning how to look past dust without ignoring it, using it as both an impediment and a diagnostic tool. Seeing the invisible. Multi-wavelength astronomy. The greatest breakthroughs in Milky Way astronomy came when astronomers learned to observe the universe beyond visible light. Radio, infrared, and X-ray astronomy opened windows into regions previously hidden by dust and darkness. Radio astronomy. Radio waves pass through dust with little attenuation, making them ideal for mapping cold gas and large-scale structure. Observations of neutral hydrogen revealed the galaxy's rotation, spiral pattern, and enormous gaseous extent. Molecular gas, traced through radio emissions of molecules such as carbon monoxide, pinpoints star-forming regions embedded deep within spiral arms. Infrared astronomy. Infrared light penetrates much of the dust that blocks visible wavelengths. Infrared surveys unveiled the dense star fields near the galactic center and allowed astronomers to measure stellar populations across the disk and bulge. Many stars that are invisible optically become prominent in infrared images. X-ray astronomy. X-rays reveal the most energetic processes in the Milky Way. Supernova remnants, accreting black holes, neutron stars, and hot gas in the galactic halo. Toward the center, X-ray observations expose activity that would otherwise remain hidden, offering insight into extreme environments. Together, these wavelengths provide a layered view of the galaxy: cold gas, warm dust, stars of different ages, and high-energy phenomena, all contributing to a more complete picture. The Gaia Revolution. One of the most transformative developments in Milky Way studies is the European Space Agency's Gaia mission. Gaia is designed to measure the positions, distances, and motions of stars with unprecedented precision. Gaia has already catalogued over 1 billion stars, providing accurate distances and proper motions for an enormous fraction of the Milky Way's stellar population. For the first time, astronomers can study the galaxy not as a static snapshot, but as a dynamic system in motion. These measurements allow researchers to map the three-dimensional structure of the disk, bulge, and halo, track stellar orbits and velocity distributions, identify coherent moving groups and streams, infer the galaxy's mass distribution and gravitational potential. Gaia's dataset is so rich that it will continue to fuel research for decades, reshaping nearly every aspect of galactic astronomy. Galactic archaeology through motion. Stars carry with them the memory of their origins, not in their appearance alone, but in their motions. By analyzing how stars move through the galaxy, astronomers can identify remnants of past mergers and accretion events. Gaia's kinematic data reveal stellar streams, elongated groups of stars moving together through space. These streams are the debris of dwarf galaxies or star clusters that were torn apart by the Milky Way's gravity. Though spatially dispersed, their shared motion betrays a common origin. In addition to streams, Gaia has uncovered kinematic groups, stars with similar velocities that do not necessarily cluster spatially. Some of these groups may be the result of ancient mergers, while others reflect resonances induced by the galaxy's bar or spiral arms. This field, often called galactic archaeology, treats the Milky Way as a fossil record. By decoding stellar motions and compositions, astronomers reconstruct the sequence of events that built the galaxy over billions of years. Halo stars and cannibalized galaxies. One of the clearest outcomes of modern surveys is the realization that many stars in the galactic halo did not form in the Milky Way. Instead, they originated in smaller dwarf galaxies that were later accreted. These stars often have distinct chemical signatures, reflecting the slower and less efficient star formation histories of dwarf galaxies. They also move on eccentric, inclined orbits, unlike the orderly rotation of disk stars. By identifying these populations, astronomers have confirmed a key prediction of galaxy formation theory. Large galaxies grow through the hierarchical assembly of smaller systems. The halo is not a primordial component alone, but a mosaic of past mergers preserved in stellar motion and chemistry. The Milky Way in the night sky. Despite all the complexity revealed by modern instruments, the Milky Way remains a striking naked-eye object. From Earth, it appears as a luminous band encircling the sky, visible on clear moonless nights far from city lights. This band passes through about 30 constellations, weaving across familiar star patterns. From the southern hemisphere, it arches high overhead, revealing rich star fields and nebulae. From the northern hemisphere, it is lower but still prominent during summer months. The Milky Way's apparent path reflects the orientation of the galactic disk relative to Earth. We see the disk edge on, so the combined light of billions of stars along that plane produces the bright band. Dividing the sky. The Milky Way effectively divides the sky into two roughly equal hemispheres. One side lies toward the galactic plane, rich in stars, nebulae, and dust. The other points away from the plane toward the galactic poles, where the sky appears darker and contains fewer stars. This contrast is striking under dark skies. The galactic plane is crowded and textured, while the polar regions are sparse and deep, revealing distant galaxies beyond the Milky Way. This division shaped early astronomical observation. Many of the faint nebulae catalogued by early astronomers turned out to be external galaxies, visible primarily away from the Milky Way's obscuring plane. Dust lanes and dark rifts. Under truly dark skies, The Milky Way reveals intricate structure to the naked eye. Dark rifts snake through the bright band, particularly prominent toward the galactic center. These are dust lanes, vast clouds blocking background starlight. Historically, these dark features were sometimes mistaken for actual gaps or voids in the galaxy. Today they are understood as foreground structures silhouetted against dense star fields. These dust lanes are especially dramatic toward the constellation Sagittarius, where the line of sight intersects both the densest stellar regions and the most massive dust clouds. Photographic views of the galaxy. Long exposure photography and modern digital imaging have transformed our visual understanding of the Milky Way. Images often show a bright central bulge toward Sagittarius, a flattened star-rich disk, prominent dust lanes, subtle warping of the galactic plane. These images combine data across wavelengths and often exaggerate color to highlight structure invisible to the eye. While visually stunning, they are interpretive representations rather than literal views. Still, they provide a powerful sense of the Milky Way as a coherent structure, a disk with a luminous heart and complex texture shaped by dust and stars. A galaxy still being measured. Despite centuries of study, many fundamental properties of the Milky Way remain uncertain. Astronomers continue to refine estimates of the galaxy's total size, its total mass, including dark matter, the number and shape of spiral arms, the detailed distribution of dark matter. Different measurement techniques yield slightly different results, and uncertainties remain significant. The Milky Way's complexity ensures that no single observation provides a complete answer. Even the galaxy's spiral structure, so obvious in textbook diagrams, is still debated. Is it dominated by two major arms or four? Are some arms long-lived or transient? How do the bar and spiral arms interact? These questions remain active areas of research. The limits of knowledge. The Milky Way reminds us that proximity does not guarantee understanding. In some respects, distant galaxies are easier to study precisely because we can see them as whole systems. Our own galaxy, by contrast, must be inferred from inside. This limitation is not a failure, but a defining feature of astronomy. It forces creativity, careful modeling, and constant reassessment. Each new survey refines the picture and often complicates it. The Milky Way is therefore not a solved problem, but a living one. Its study evolves alongside technology, theory, and data. Perspective and cosmic humility. There is a philosophical dimension to studying the Milky Way. For centuries, humans believed Earth lay at the center of the cosmos. Later, we learned that the Sun is not central, that the Milky Way is one galaxy among many, and that even our galaxy is part of a vast cosmic web. Observing the Milky Way from within reinforces this lesson. We are participants, not observers from afar. Our planet, star, and species are embedded in a system far larger and older than ourselves. Yet through science, we have learned to transcend our limitations, to reconstruct a galaxy we cannot step outside of, to map motions across tens of thousands of light years, and to read history written in starlight.